Hi, I am Rayat Imtiaz Hossain, and I'm going to present our paper titled Visual Prompting for Generalized Few-shot Segmentation and Multi-Scale Approach. Before I explain our paper, I'd like to briefly define the generalized few-shot segmentation. So in a standard few-shot setup, the data is usually divided into two disjoint sets, the base categories and the novel categories. The model is usually trained with base categories first, where it sees a lot of examples of the base categories. And then during the test time or inference time, it is given a few examples of novel categories in the support set, and the model is expected to segment only the novel categories. However, in the generalized few-shot segmentation, the model is not only expected to segment the novel categories that it sees from the support set, but it's also expected to retain the performance of the base categories that it has seen during the base training. So existing literature has shown that the transformer-based models can be prompted for few-shot inference. However, it is relatively underexplored whether such models can be prompted for dense prediction tasks like semantic segmentation. Therefore, in this work, we like to address a couple of questions. First, how we can prompt transformer decoders for few-shot image segmentation. And the second is that whether we can train such models and prompt them in a manner such that it can retain the knowledge that it has learned during the base training or from the base model. In this work, we made a few key contributions. First, we prompted a multi-scale transformer decoder by means of learnable visual prompts, which we were able to learn from few-shot demonstrations. Second, we proposed a novel to base causal attention mechanism that learns the relationship between base and novel prompts and leads to a better feature separation of novel prompts. Third, we were able to use the unlabeled target image and the predictions of the unlabeled target image to further fine-tune the visual prompts in a transductive manner to improve the performance. So in this slide, we see our proposed architecture. So this model is first trained on base classes or base categories using large amount of data. And the base model is trained using cross entropy loss. During novel fine-tuning stage, we add the following components: the novel prompts, the novel to base causal attention mechanism, and novel classifier. So the novel prompts are initialized using average pooling of the support set features using the ground truth masks. Then the novel prompts are defined by novel to base causal attention mechanism. All the prompts then interact with image features at multiple scales. And finally, the refined features, the image features, and the classifier is used to predict the final segmentation. So in this slide, we see the quantitative performance of our approach and compare it against state-of-the-art DM. As you can see, our approach without transduction outperforms DM with transduction on both dataset. And when we add transduction on top of our approach, we see there is a further improvement in performance. Here we see the qualitative results and compare our approach with DM. As you can see, the causal attention improves the overall segmentation accuracy. And you can see our approach is better on the examples that are given here compared to DM. So we have seen that the transformer-based frameworks can be prompted at multiple scales to achieve state-of-the-art performance on generalized few-shot segmentation, and that our proposed causal attention mechanism can lead to better separation of novel and base category prompts and therefore an improved performance. Thanks, everyone.